In this lesson, we're going to talk about actually determining whether a function is a linear function or a nonlinear function. Once you've established that it is a function, that a relation is a function, then your next step is to determine, okay, is this going to be linear or is it nonlinear, and how can I tell the difference between the two? Well, in this, I've given three different things all right here together, and we're going to talk about all of them. For example, I see this equation, y equals negative 2x plus 5. And over here, I've actually graphed what that would look like. But here, I want to look at, just like start with the table. We've been talking about how to find slope and actually finding the rate. And I'd had you finding all of them, even though you could just choose two. And here's why. Just like what we've been doing, if I want to find whether this is going to be a linear function or not, if I have a table, I can look at the rate. For example, 7 to 3, I'm actually subtracting 4. 3 to negative 1, I'm subtracting 4. Negative 1 to negative 5, the difference again is negative 4. And if you notice on this one, it stays the same. So let's look at our input values. Negative 1 to 1, that's a difference of plus 2. 1 to 3, again, plus 2. And 3 to 5 is, again, plus 2. So when I look at my output, all the rate is exactly the same. Then I look at my input. It's exactly the same throughout the entire table. So in this case, that's called a constant rate of change. It's constant, the exact same. So here, I want to fill in the blank. I want to say linear functions have a constant rate of change. They stay the exact same throughout. The output remains the same. The input remains the same. So again, when I look at the equation, anytime I see an equation that is in slope-intercept form, so when I look at this, because when I actually take the slope, negative 4 divide over positive 2, I get a slope of negative 2. Positive divided by negative makes it a negative. So I look at any equation I see that's in slope-intercept form, I can automatically know that it is a linear equation. So, and even, for example, even if I see an equation that's in standard form, say if I saw 3x plus 2y equals 12, I can take that and I can put it into slope-intercept form. So therefore, again, this is going to be a linear function. So equations in slope-intercept form are linear. When you actually graph them, they will be linear. Anything that's going to in slope-intercept form, or if I can transform it into slope-intercept form, say from standard form, it's going to be linear. And then, of course, when I look at the graph of actually a line that's graphed, in this case, this is just simply this equation and these coordinate pairs along the way. All that I notice is that line is a straight line. So unless it's an undefined slope, you're looking at a straight line. A linear line is straight when it is a linear function on a graph. So a linear function is a straight line when graphed. So the next thing we're going to look at is actually what a nonlinear function will look like. All right, since we've established what makes a relation a linear function, we have to determine again now, is it a nonlinear function? Again, just a reminder, this is once we've established that the relation is a function. It's just a matter of if it's a linear function or a nonlinear function. So let's look at this. Well, the difference here is it's in slope-intercept form except for one thing. You've got the exponent over the x, or over the variable, and that's important because when the exponent is over the variable, it changes everything. For example, if it was over the one that's understood to be here, well, you can get 1, and if it's placed over the 2, that's not a big deal. It's still linear, but it's placed over the variable, which changes it to nonlinear. So when you have an exponent over the variable that looks to be in slope-intercept form, it is nonlinear. And how do they come up with this, and how do they come up with the table versus this? I'll give you one example just so you can see how that actually works, and then we'll talk about the rate of change. So for example, I'm just going to choose, let's go with the first here. For example, it's saying negative 2. I'm just going to put in the numbers for the variables. Equals, well, the negative of x squared, which is negative 2 squared, plus 2. All I did again was put the numbers in where they go, and now I just solve it. So negative 2 would equal, well, negative 2 squared because exponents come first before any multiplication. Negative 2 squared is positive 4. But it wants the negative, and then when I multiply that, I get negative 4 plus 2. So in that case, negative 2 equals, well, negative 2. So in this case, that is why your y equals negative 2. So, and it's the same process all the way down. I'm just putting numbers in for the x and the y and getting my y values. So even if I didn't give you part of the y value, you could figure it out based upon the equation. But let's just look how we would determine linear versus nonlinear. When it was linear function, we had to look at the rate of change, and we said, you know what, it had to have a constant rate of change. All of my outputs had the exact same rate of change, and then all of my inputs had the exact same rate of change. Well, in this case, I look from negative 2 to 1. That would be a plus 3. You added 3 to negative 2 to get 1. But then from 1 to 2, you have plus 1. And then from 2 to 1, you have minus 1. And then 1 to negative 2, you have minus 3. Well, that's not constant. It's different rates throughout it. The thing, there's a couple different rates there, but let's look at the inputs just to show. Negative 2 to negative 1, you add 1, and then add 1, add 1, and then add 1. But even though all of my inputs have a constant rate of change, my outputs did not. So therefore, that's going to be a nonlinear function. So nonlinear functions do not have a constant rate of change. They have various rates of change. It could be all constant except for 1, and that changes it to nonlinear. So in this case, nonlinear equations can have an exponent over the variable, and that's important that you pay attention to that, over the variable, because it does change when you put it over the variable. Now, I did show a picture here of the graph. All I did was graph the equation, or I took the coordinate pairs, and in this case, when I have an exponent over the variable, I'm just going to take the coordinate pairs and graph them. It makes it so much easier. So when I look at this, when I actually graphed it, I come up with this line. This is not a straight line at all. So in this case, but it's still a function, but it is a nonlinear function. So a nonlinear function is not a straight line when it's actually graphed. It's going to have some curves. It could be one of those squiggly lines. It's still a function. It's just not a linear function. All right, a couple other looks you may see that are still nonlinear that I'm not necessarily going to go into detail right now. But for example, I may see y equals the absolute value of x, say plus 2. I may see that, but when I see absolute value around my variable, I know it's going to be nonlinear. And something else I may see that's a nonlinear function. For example, I might see y equals, say, 6 over x. And with my variable as my denominator. Again, it can be a function, but it's just a nonlinear function.